Mars is a planet of extremes. Martian winds generate global dust storms with velocities of up to 30 meters per second, capable of obscuring nearly the entire surface of the planet for months at a time. These landscapes mirror the driest places on Earth. The wind-sculpted dunes of the Namib Desert in Namibia follow the same geological processes of weathering and erosion found on the Martian surface. To investigate this terrain, we rely on the Curiosity Rover. Curiosity is a robotic geologist equipped with 10 scientific instruments designed to search for evidence of life-friendly conditions within ancient Martian rocks. When Curiosity drilled into the John Klein rock target, it revealed a significant contrast. While the surface is a rusted red, the powder excavated from the drill hole is a pristine, unoxidized gray. This gray dust indicates that the rock's interior has been protected from the harsh surface environment for billions of years. To find out if this interior ever supported life, we have to look back at the specific habitable environments that existed on Earth 3.5 billion years ago. The Earth of the Archean Eon was an alien world. The atmosphere lacked oxygen, consisting instead of a mixture of methane, ammonia, and water vapor. Laboratory experiments show how these chemicals react. When a spark simulates lightning in this primitive atmosphere, the reaction produces amino acids, the essential components of all living organisms on Earth. Deep-sea hydrothermal vents offer an alternative birthplace for life. These black smokers release ion-charged solutions through hollow chimneys, creating the weak electrical charges that may have powered the development of early molecules. The oldest potential fossils on Earth date back 3.5 billion years. These are stromatolites, concentric ring patterns formed by colonies of microorganisms that were preserved within sedimentary rock. These ancient environments suggest that life depends on a precise overlap of physical conditions: liquid water, a neutral pH, and a supply of carbon, hydrogen, nitrogen, phosphorus, and sulfur. For decades, data suggested the global surface of Mars was too salty and acidic for microorganisms. It was widely assumed that any ancient liquid water on the planet would have been toxic. The Phoenix lander challenged that assumption when it analyzed polar soil in 2008. The sample revealed a neutral pH, an early indicator that some Martian environments were chemically favorable for life. Curiosity expanded on this at Yellowknife Bay. The rover identified ancient streambed gravels and muds that were deposited in a stable, long-lived lake billions of years ago. This compares Earth's requirements for life to Curiosity's drill readouts. The Yellowknife Bay lake lacked strong acids and had low salinity. Its rocks also contain the essential building blocks of life: carbon, hydrogen, nitrogen, phosphorus, and sulfur. Finding this specific chemical combination confirms that ancient Mars possessed the habitable conditions required to support the same simple microbes that first originated on Earth. Confirming a habitable environment is a technical milestone, but it is not the discovery of life itself. We know the conditions were right, but the physical remnants of ancient organisms have yet to be found. Mars likely supported these conditions over 3 billion years ago, before its atmosphere became less dense. As the air thinned, the water evaporated and became trapped in polar ice or hidden underground. Our new targets are visible in orbital images like this. These are evenly bedded sedimentary layers that preserve a chronological record of periodic changes in the Martian climate. These sedimentary beds are the prime candidates for future sample return missions. They are the most likely places to find preserved organic compounds that could finally prove the existence of extraterrestrial life. Because of the rovers, the search for life on Mars has shifted from a general survey to a targeted investigation of the planet's remaining geological records.